Okay, let's take a look at number 10 here in section 10.1. We're going to determine the limit of this sequence. The sequence nth term is n raised to the 2 divided by n power. So it's kind of an interesting sequence here. When I take the limit as n goes to infinity, notice the form. The base n is clearly going to infinity, but 2 divided by n, right, that ratio, 2 divided by something going to infinity is going to 0. This is an indeterminate form, right? Uh, the exponent is getting closer and closer to 0, and any number raised to the 0 power is 1. And so the exponent is trying to get this limit to be 1. However, as n goes to infinity, even though this exponent is getting closer and closer to 0, it's always actually, for any fixed value of n, it is a positive quantity, right? It is positive quantity, and n is getting larger and larger in absolute value. So as n gets bigger and bigger, raised to any positive power, that is trying to make it go to infinity, right? So n is going to infinity, trying to make the expression go to infinity, but the exponent going to 0, trying to get it to go to 1. So is the limit 1? Is it an infinity, or is it something in between? Well, in order to do these limits, we've got to involve logarithms or properties of logarithms. I like to do it this way. I'm going to let y be the limit we're looking for. So y is the limit as n goes to infinity of n to the 2 divided by n power. And then I'm going to take the natural log of that. Natural log of y will be the natural log of this limit. And I can push the natural log past really inside this because the natural log is continuous on its domain, and we're certainly on its domain since n is going to infinity. So I can essentially push the limit through going this way back here, or vice versa. Now I'm going to use the property of logarithms. Remember, if I take the natural log of some expression raised to an exponent n, this is n times the natural log of a. So that's a property of logarithms we use quite a bit. So I'm going to bring this exponent down in front, and I have it here. Sorry, I made a little mistake there. So limit as n goes to infinity, right, of this expression. And I'll just rewrite this 2 over n times this is 2 natural log of n over n. Now, as n goes to infinity, the natural log function is going to infinity, and so is n. So now, look what form we're in. Still indeterminate, but unlike this indeterminate form, this one we know what to use, right? What do we use with this limit form? Hopefully, we're going to use L'Hopital's rule. So by L'Hopital's rule, this is limit as n goes to infinity. What's the derivative of the natural log of n? 1 over n. Of course, the derivative of n is just 1. And then as n goes to infinity, obviously this fraction here is going to 0. 2 times 0 is going to 0, and 0 divided by 1 is going to 0. Okay, so this limit is 0, but remember, this is not the limit we were looking for. This is the natural log, right, of the limit. Here's the limit we're looking for. We called that y. We found the natural log of y. So if the natural log of y is 0, then y must be e to the 0 or 1. And so the limit of our sequence is actually 1. And so in this case, 1 wins out. The exponent, in a sense, overpowers the base. Okay, hope this is helpful.